It's my great honor to introduce Professor Ken Freeman. He's an extremely distinguished scientist, having been awarded Australia's Prime Minister's Prize and the American Astronomical Society's Henry Norris Russell Lectureship. And these are only in the past few years. If I went and enumerated his awards and accomplishments, I would eat up into his time. So I will continue. He studied math and physics at the University of Western Australia, then went to Cambridge. Following his PhD thesis, he returned, after a brief stint in Texas, I believe, he returned to Australia, where he has basically been at the Australian National University, or Mount Stromlo, for the majority of his career. His early work was in analytical models of galaxies and spiral galaxies, and in 1970 he was one of the first to point out the missing matter, this dark matter in galaxies. His most recent work is in star formation history, looking at the chemistry within galaxies through galaxy evolution. And in looking at his CV, his curriculum vitae, his life's work, the thing that I'm most amazed with is the 54 PhD students, maybe more now, that has gone through. This is the idea of being so active in the field to keep that much research going and then to have that impact on the numbers of students' lives. And of course, that's one of the reasons we're here at Sonoma State, is to have impact on students' lives. So very impressive that Dr. Freeman has had 54 PhD students through his research and his career. Let's give a warm welcome to Dr. Freeman.
Well, thank you very much, Scott. It's very kind of you. So my score of PhD students has gone up to 56. Okay, so I want to talk to you today about dark matter in the universe, but I also want to thread into this discussion just a few words about the nature of astronomical discoveries, because there's some pretty weird things happened in the whole story of dark matter, and I just wanted to share some of those with you. It's only just a little bit of it. So here's a little introduction to that part of it. The process of scientific discovery doesn't always go in a straight line. Sometimes it staggers along, sometimes going in the right direction, but for the wrong reasons. And some of these discoveries that people make, which we look back at and we see that these were really major discoveries, were far ahead of their time and they were ignored. And for some reason the scientific community wasn't able or not ready to absorb these new ideas. And I've been fascinated by this process about why this happens. And I just wanted to at least give you my view on this as we go through this story of dark matter. So the talk is about the discovery of dark matter in the universe. The universe, as I'm sure you all know, it's made of stars and galaxies that we can see with our telescopes. Here's an example of a star-forming site in our own galaxy. Here's a whole galaxy, nice spiral disk. But this is only a small fraction of what's actually in the universe. There's about 6 times more mass in the universe that we can't see. And that's this mysterious, invisible dark matter that pervades the entire universe. We know it's there because we can measure its gravity, and I'll tell you more about how we measure gravity. Measuring gravity is actually relatively straightforward. But whatever this stuff is, and there's an awful lot of it, we don't know what it is at this point. So it's a story, the discovery of dark matter, it's a story of great discoveries that were ignored for decades, ideas that turned out to be right but for the wrong reasons, and the gradual realization that dark matter is just not an interesting phenomenon. It actually determines the entire structure of the universe in which we live. Without it, our universe would be completely different. And we, in fact, may not be here. It's as serious as that. So dark matter and spiral galaxies, these are the ones I'll talk about mostly, except right at the end I'll talk about other galaxies. I talk about these because they're rather simple dynamically. It's very easy to measure gravity. So these are flat objects and they're spinning. So here's one you're seeing face on, like a dinner plate. Here's one that you're seeing edge on, probably a rather similar galaxy. You're seeing this one edge on, so it's just as if you're looking at a dinner plate, edge on. And these are the most common kinds of galaxies in the universe. But as I'll say this many times, you'll be really sick of me saying this. What you see here is only about, in this case, for galaxies, it's even a smaller fraction. What you're seeing here is only about 3% of the total mass. The other 97% of the mass of these galaxies is in this dark form that we don't really understand too well. So the story started with a man called Fritz Zwicky, and he discovered dark matter in the Coma cluster of galaxies way back in 1933. So what Zwicky did, he used a 100-inch on Mount Wilson, and he looked at this relatively nearby cluster of galaxies. Now, almost every object in this picture, except for this thing, is not a star, it's actually a galaxy. So in the Coma cluster, you have about something of the order of 1,000 galaxies, and they're all buzzing around in each other's gravitational field. So what Zwicky realized, if he could measure how fast just even a few of these galaxies were moving relative to each other, you could see how big this thing was, and then you've got all the information you need to measure how much mass there is in this cluster. So that's what Zwicky did. He measured 16 galaxies in the Coma cluster of galaxies. He then did a calculation, which is exactly the sort of calculation we would do today, and he got, as far as we can tell, he got everything right, and he showed that there was much more mass in this cluster than we would expect just from the stars in the galaxies alone, by about a factor of 20. A word about Zwicky. He was a very interesting character. I'll say a few more words about him in a moment. He was a cantankerous and difficult individual. I met him just towards the end of his life when I was a postdoc, but he's certainly one of the great scientific geniuses of our age. So Zwicky was actually born, his parents were Swiss, but he was born in Bulgaria. And I'm interested in Byzantium, and I made a trip to Bulgaria just a few months ago. And I went to this place called Varna, which is right on the Black Sea, and that's where Zwicky was born. And we went to the house in Bulgaria where Zwicky was born. It's quite a nice house. And there's a plaque in Bulgarian and in English, and it says, in this house, or in this home, was born Fritz Zwicky, the astronomer who discovered neutron stars and the dark matter in the universe. And you couldn't put it better than that. He's an amazing, amazing individual. The dark matter was an observational discovery. Neutron stars were a sort of more or less theoretical thing. But he's absolutely right on both counts. And he did a whole bunch of other things which a lot of people still argue about. So Zwicky's discovery of dark matter in the Coma cluster, 1933. His data were accurate. His analysis was the same as we would use today. He showed that the mass of the Coma cluster is at least 10, it's closer to 20 times larger than the sum of the masses of the individual galaxies. This paper came out, first of all, in a rather obscure Swiss journal in 1933, but then it came out again in English in 1937. This profound discovery got little response other than some follow-up observations by another astronomer who looked at another cluster of galaxies, the Virgo cluster, and got a similar result. Apart from that, there was almost no reaction to this. It took another 35 years for the idea of dark matter to take off, but Zwicky did get the credit in the end, which of course doesn't always happen. And it really fascinates me why a discovery like this doesn't really stir the place up. And you can contemplate why that might be. I mean, if somebody came along today, if we didn't have our background and said, okay, well, there's 20 times more mass in the Coma cluster than we thought there was, what would you do? I mean, if you have nowhere to slot a discovery like that in, what do you do? Of course, you just ignore it. And this keeps on happening with discoveries that people can't find a way to fit into their current knowledge or extensional knowledge. But anyway, more on that in just a second. Okay, so why did Zwicky's profound and apparently straightforward discovery get so little response? Well, a number of possible reasons. Zwicky was a well-known maverick, oddball, what we call in Australia a ratbag. Did the community already regard him at that early time in his career with suspicion, or did that come later? It certainly came later in a big way. I mean, people were very suspicious of Zwicky later in his life, despite his brilliance. Or was it due to suspicion of results for which there's no existing theoretical framework. And I suspect, unfortunately, that's the truth. There's a truly preposterous statement that Sir Arthur Eddington is claimed to have made. He was a theoretician, and his view was that it's a good rule not to put overmuch confidence in observational results until they're confirmed by theory. I'm glad to hear you laugh, because I find this completely preposterous. It should be absolutely the other way around. But there's still, this sort of view, unfortunately, is still very pervasive, particularly in cosmology today. Because if people observe something that's not consistent with the current batch of simulations, which of course are themselves evolving, it's regarded with great suspicion. So I think there's a lot to do with that. There's another point made by Stigler, and his statement was that big new ideas only tend to catch on when the scientific community is ready for them, which is basically what we're saying here, or a different element, an established scientist finds a use for them. So if some established scientist, somebody who's already famous, says, yes, that's exactly the result I needed to make sense of something else, publishes that, then the idea takes off. Without that sort of support, these new ideas often tend to just sit. Okay, so there's another one of these. Zwicky's one's not the only one. This one in some ways is even more egregious because it came much later, 1959, and it was by two people who were enormously respectable. Franz Kahn was my thesis supervisor, thesis examiner. Franz Kahn was my thesis examiner, which immediately bestows a certain respectability on him. Low Volcher was far more respectable even than that, because he was Director General of ESO, and he is the Director General under whose rule the VLT projects came along. So he's a great scientist. They wrote a paper, a very simple paper, on the motion of Andromeda relative to our galaxy. And this is another very important paper that fell flat at its time. So the story is very simple. In fact, I'm going to slip forward at the slide. Here's our galaxy, as it's seen from the Earth. Here's M31, the Andromeda galaxy. They're 2.3 million light years, 750 kiloparsecs apart, and they're coming at each other at 118 kilometers a second. Now, what's unusual about that? Well, you know the universe is expanding, but here are two galaxies coming towards each other. Why is that? Well, the reason is they would have started together as part of the expansion, expanded, but there's so much mass in these two galaxies that the gravitational attraction locally turns around the expansion of the universe. They stop, they get to a point that's called turnaround, and then they start to collapse in on each other. So you have all the information, you have the distance apart, you have the velocity, you have the age of the universe, which these guys already have a pretty good idea of, and so you've got all the information to work out what the masses is. It's a very simple calculation. A first-year physics student could get this pretty right. So the outcome is that the total mass of the pair is about 20 times larger than the stellar and gaseous mass put together. Again, this factor of 20 keeps on coming up. So the argument was direct, it's compelling, it's accurate by modern standards. There are a few observational things that they had to assume, which have actually been measured now with Hubble and turned out to be correct. But this very important paper, and a very direct estimate of, now this time, not dark matter in a cluster, it's dark matter in a couple of galaxies. It made almost no impact back in 1959. And that's curious, because why did this paper have so little impact? Well, as I said, the argument's simple, correct, it survived to the present, very respectable, well-regarded researchers. It should have started the dark matter revival in 1959, and it didn't. And my guess is that, again, in 1959, there was just no framework in which to slot an observation like this. Somebody comes along and says, well, it's 20 times more mass in Andromeda and our galaxy put together than you thought. And you've just got no way of managing this information. So what happened then was that the subject sort of sat dormant for about 10 years, and then the radio observations of spiral galaxies in the early 70s indicated that spiral galaxies are actually enveloped in massive extended halos of this dark stuff. The argument at that time, which I was part of, was no more convincing than what Franz Kahn and Low Volcher did, but it made an impact, and the subject took off. So why? Well, by 1973, there was a theoretical framework into which to slot this stuff, even though it turned out subsequently to be wrong. So in this case, the theory turned out to be irrelevant, the people believe observations that fit into the theoretical framework, even if the observations have a sounder basis than the theory. It's a strange business. It allows them to come to grips with startling observations. I'll tell you a little bit more about that as we go on. So, now just a little bit about how we actually measure gravity. Well, dark matter is dark, so we can't see it. All we can do is measure its gravity. How do we measure gravity in a galaxy? For spirals, it's simple. They're flat things and they're spinning around. We can measure how fast they rotate and thereby measure the gravitational field anywhere in the galaxy. So just a tiny bit of algebra here. Say the stars and gas in the galaxy at some radius r, say, are going around in a circle at some velocity v. If you want to go around in a circle, you need an inward acceleration. If you haven't got that inward acceleration, you're just going to go off in a straight line. So to keep bending around, you need an acceleration. Where does that acceleration come from? Well, if I had a weight on the end of a piece of string, I'd be swinging it around my head. The weight would be going around the circle, and the acceleration is coming from where? The string. Can you be a tiny bit more specific?
Your arm.
No, not mine. Yeah. What is it about the string that's keeping that weight going around?
The tension.
Tension. Thank you. That's it. So it's the tension in the string. In the galaxy, the force to produce the acceleration is just the inward gravitational force in the galaxy. So this particle here is seeing the gravitational force primarily of the matter inside it. The matter outside it doesn't do very much. It's the matter inside. So I can easily, if I can measure how fast that's going around, I can straight away tell you what the gravitational force is there. And that must come from the gravity of everything. And that's really all there's to it. It's truly as simple as that. So this is what we now know about the rotation curves of spirals. So I'm plotting a graph here. This is the velocity of how fast material in the galaxy is going around, and this is distance out. And 20 kiloparsecs would be around about here in a galaxy like this. So what we see, now we measure this with radio telescopes. Just look at the hydrogen in these galaxies. This is what we observe. So the rotation rises and rises and rises. And so this is in velocity, not in angular velocity. Rotation rises and rises, and then it goes flat. This is what we expect from stars and gas alone. We can calculate that. And that was my contribution in around 1970. I calculated for the first time how spirals should be rotating, assuming all the mass was in gas and stars. And it didn't compare very well with the rotation data, indicating there was a lot of extra invisible material. But at that time, the radiosynthesis telescopes were only just coming on air. The data were poor, and the idea of dark matter remained pretty controversial until around the end of the decade, when suddenly much better data became available. I'll tell you about that in just a second. Now, it's the difference between the gravity associated with this observed circular motion and the gravity associated with what we expect. That's the dark matter contribution. Okay? So that was the very clear indication that there's much more to these galaxies than we think. Okay, how do we measure rotation? We use telescopes like this. This was the one that the real clinching observations were made. It's a telescope in the Netherlands. It's 14 antennas. You make interferometers between each pair, and as the Earth rotates, you build up an image of this galaxy with the resolution that you would have had if you had a single telescope with that sort of diameter. So these are great for measuring how fast hydrogen's moving. Spiral galaxies have a lot of hydrogen moving around in circles around the centre of the galaxy, ideal for measuring how the rotation rate changes with radius, which is what we need. Okay, so the big thing that happened in 1978 was that this chap's thesis was published. This is a friend and colleague of mine. His name is Albert Bosma. He was the first person to produce really good rotation data with this new Westerbork telescope. And when his thesis came out, it absolutely stopped. The argument just stopped because the data were great. There was no question about the problems that we had. His thesis was very influential and was quoted so much. His name's Albert Bosma. The people thought his name was Bosma's thesis. The people kept on saying Bosma's thesis, Bosma's thesis, and that's him. And that's his thesis, actually. The front page of his thesis. So, okay. So, the Kahn and Bolcher work, going back to our galaxy in Andromeda, that was dynamically very straightforward. So is the dynamics of the rotation curve analysis. One of them made an impact and the other one didn't. And the idea of dark matter from rotation curves started controversially around 1970 because the data was poor, but it was taken seriously. And why was it taken seriously? Well, in the 1970s, the idea of having a massive dark halo around galaxies, it got some unexpected support from theoretical arguments by Jerry Ostrander and Jim Peebles. And his arguments, their arguments were that to stabilize galaxies against forming bars, you needed dark matter. So what does that mean? Some galaxies have a sort of elongated structure in their inner parts, and they're called bars. In 1973, these were regarded as a rarity, and most galaxies were believed not to have them, and you had to find some way to stop those things from forming, and they form very naturally. And one way to stop bars from forming is to invoke a big envelope of dark matter, completely independent argument. Now those arguments turned out to be irrelevant because it's turned out now that most galaxies in fact do have bars. We know that about more than 70% of them have bars, and in fact to sustain bars we need dark halos. It's exactly the opposite way around. The whole theory is completely turned upside down. Anyway, the controversy ended in 78. So even though the theory turned out to be irrelevant, people believe observations that fit into a theoretical framework, even if the observations have a sounder basis for the theory. Okay, so just a tiny bit more on barred spirals. Here's the same one that you saw. Here's one that isn't barred, and people thought they were rare, and you needed dark halos to stop them from forming. This was all wrong. Now we know they're very common. About 70% of disk galaxies, including the one we live in, have some kind of a central bar. I'll just show you one more picture of a galaxy, M83. It's a big galaxy in the south, about 4 megaparsecs away. Here's a picture in blue light. Pictures are printed negative, black stars in a white sky. This is in blue light, so the blue stars in the spiral arms and the dust are both very prominent. When you go to the infrared, 2.2 microns, the dust becomes transparent. The blue stars don't contribute very much. Same galaxy, same scale, and you see that straight away there's a very visible bar. And that's really what changed this whole subject, that the bars are really very common. Okay, so here's the situation, just a sketch about the dark matter situation. We now know that it extends 5 or 10 times further out than the stellar disks of the spirals. Makes up about 97% of the galaxies, and about half of dark matter in the universe is in galaxies in these halos, the other half's out in intergalactic space. Okay, so rotation's been measured now for several hundred galaxies. We always find the gravitational field is much stronger than expected from the stars and the gas alone. The stars and gas provide only about 3% of the gravitational field. What is this dark matter? We don't know. It's one of the big problems of astrophysics today. As I mentioned earlier, this is not just a thing of sort of passing interest for galaxies. It affects the entire structure of the universe. The discovery of dark matter in galaxies in the 1970s changed our ideas about how galaxies form from dark matter and gas early in the universe. So our understanding at the moment is that early in the life of the universe, very early, just after the Big Bang, the distribution of matter was fairly smooth, just with very small fluctuations of the order of 1 part in 100,000. And these fluctuations, they just grow naturally under the influence of gravity. So if you have a slight overdensity, that overdensity grows gradually because of gravity. If you have an overdensity that's a bit elongated, its gravitational field on the short axis is stronger, and you finish up with all this sort of filamentary structure that just grows quite naturally, just under the effects of gravity only. This paradigm is called the cold dark matter paradigm. It's cold because we can't have this stuff with very large random motions, because otherwise it would never condense into galaxy-sized lumps, and we'll come back to that a little bit later. So this paradigm for the evolution of the universe, it was invented in the early 1980s as a result of the, once people agreed there really was dark matter in galaxies, and it's still our working paradigm today. So cold dark matter remains the paradigm. This is a computer simulation, but its properties are very similar to the real universe. Okay, I just want to tell you about one problem with this whole paradigm, and it's called the substructure problem. So I'm going to jump forward one and I'll come back. Now I'm just talking about computer simulations here. So this is a simulation of a halo like perhaps the halo of the galaxy that we live in. So this whole thing would be the halo of our Milky Way, but you can straight away see it's pretty lumpy. You've got big lumps, and then the big lumps themselves have lumps, and there's a hierarchy going right down to Earth-sized masses, that lumps within lumps within lumps. And these simulations give far more small subhalos or lumps relative to the numbers of small galaxies that we see. So this is the problem. From simulations, we expect a galaxy like ours, if it's a big galaxy, to have about 500 satellites with masses more than, say, 10 to the 8 times the mass of the Sun. We don't see those. We see about 40. What's wrong? Well, it could be that there's a whole lot of these satellites are just dark. They've got dark matter, but they don't have enough ordinary matter, which we call baryons. Or there's some problem with the whole dark matter paradigm. And my belief is that it's probably this one here, that there are a lot of lumps out there, but they just don't have any baryons in them to light them up. Okay, so people are searching for more satellites, and they're gradually finding a few, but I think it's very unlikely that we're going to find another 400. A few years ago, we made a survey in neutral hydrogen of the whole southern sky using this large single antenna. What we were expecting to find was galaxies that had just dark matter and gas, but no stars. So we're doing really a blind survey of the sky in hydrogen. These would be nice candidates for the missing satellites. We didn't find a single one of these, not one. We found thousands of galaxies, but none of them that have only dark matter and gas. Every galaxy that we could see in gas, in hydrogen, also had starlight. we're not really sure of why these starless galaxies don't exist, but they don't appear to. Excuse me. Okay, so there is an alternative to dark matter that's been around now for about 30 years, and that alternative is called modified gravity. And the idea is very simple. It's just that Newton's inverse square law of gravity isn't quite right. Now, you know what Newton's inverse square law just means that as you go away from a gravitating object, the gravitational field drops, but it drops like the square of the distance that you're away from the object. Well, why should this be? Why shouldn't Newton's law work? It's well tested in the solar system, and it seems to work just fine. That is true. But when you get into galaxies, you've got big velocities, but you've got these enormous distances. Remember, the acceleration is v squared over r. And because r is so big, the acceleration in galaxies gets very low. In fact, out here in this galaxy, it's about 100,000 times lower than the acceleration that Pluto experiences as it goes around the Sun. So we're in a domain where, in galaxies, where Newton's laws haven't really been tested. And it's possible that they don't work so well, or it doesn't work so well. Well, what would we have to do? How would we have to change Newton's law to make galaxies rotate like this, flat, instead of like this, dropping off like that? Okay, this all goes back to a chap called Milgrom in 1984. He just said, all right, well, the acceleration we need to go around the circle is v squared over r. From Newton's law, we just shuffle these things around. Here's the acceleration. It's mass divided by radius squared. So v squared over r, the acceleration we need, it's got to be proportional to mass over r squared. And shuffle this around a bit, and you find the velocity drops off like 1 over the square root of r. And that's pretty much what we're seeing here. Okay, so Milgrom said, all right, well, let's just make an assumption. This force law changes when the acceleration is below some low acceleration, we'll just call it a0, it's just some number, but it's low. And he proposed that the acceleration changes from 1 over r squared, or mass over r squared, to mass over r when you get to this low acceleration. Well, I'll do the same algebra, v squared over r is the acceleration, the force is now m over r, and then you can see you just cancel out the r's and v is constant. So v would be approximately constant with radius, like we're seeing here. This has been a very difficult idea to disprove. People tried very hard to discredit it. It's still sort of around, not perfectly. It's got its problems. I don't know if I'll get to this or not. But at the time, it was just an assumption. Now it's got a relativistic framework. That doesn't mean it's right, but it has really been very difficult to prove wrong. And because of the problems with CDM, like there's too many satellites problem, and there are a bunch of others that I won't tell you about, some people are actually taking MOND much more seriously than they used to. Okay, now I'm going to talk a little bit now about the density of dark halos, because this is something, A, I've been working on, and B, I think it's actually quite interesting. So what we're trying to do is measure how dense the inner parts of dark halos are. Well, why is that interesting? Well, the density of the dark halo reflects the density of the universe at the time that the dark halo was formed. So, after the Big Bang, the universe is expanding, little bits of material condense out and they become the galaxies that we see now. We believe that the smallest galaxies formed very early in the universe, and the big ones, like the Milky Way, formed much later. Now, if that's true, then we would expect the small galaxies to have very dense dark halos and the big ones to have less dense dark halos. And the question is, do we see this? The answer, of course, is yes. I'm telling you a story. All right, so how do we measure densities of dark halos? Well, when we have a rotation curve like this, here's what we remember: rotational velocity against distance from the centre. This is the rotation curve we observe with the radio telescope. This is what we can account for in terms of what we can see. So the rest of it has got to have a shape a bit like that. And that's the inferred rotation curve of the dark halo. If you measure the slope of a rotation curve on dimensional grounds, that is a density. It's as simple as that. So we just have to measure that slope. And we straight away get what the density in the center of the halo is. It's all, again, all very simple. My colleague John Cormody and I have been working on this for some years. And we use two kinds of galaxies. One is the spirals that we've talked about a bit already. And they typically have masses between about 1 billion and 1,000 billion solar masses for the big ones. Then we also tack onto that small galaxies, like the ones that we think are very dense. Now I'm going to show you two kinds of these. One are called dwarf spheroidal galaxies, which are just old stars, hard to see. And the other ones are dwarf irregular galaxies. They're messy and full of gas and young stars. But again, masses down as low as 1 million solar masses. So they're really just like big star clusters, except that they have dark matter. So here's a dwarf spheroidal galaxy. You can just see some faint stars. This one's called Leo 1. They get much, much fainter than this. These galaxies don't rotate. The stars just buzz around in the field of the dark matter. But we can estimate their masses by measuring the velocities of stars, and that's done. And it turns out these galaxies are almost pure dark matter. Some of them have less than 1% of their mass in stars. They've lost almost all of their ordinary matter, or maybe they never got it in the first place. So here's another galaxy. This is a dwarf irregular galaxy. Now, this is a gassy thing. You can see there are patches of star formation here. So there's gas, young stars, old stars, easy to see. We can study these in hydrogen because they've got the gas. Total masses down as low as 1 billion solar masses. And again, we can use how the gas is moving in these things to measure the densities of the halos. So this tiny little galaxy, it's about 10,000 times fainter than the Milky Way, but its dark matter is about 1,000 times denser, because we believe it formed very early when the universe was very dense. Okay, so I'm going to show you one of these things that are called scaling laws. There's a whole bunch of these, but I'll just show you the one. So what we're looking at here is the brightness of the galaxy plotted along the horizontal axis and the log of the halo density. So let me just explain that a tiny bit. This is a bright galaxy like ours. This is one of these very faint galaxies. And these are, again, in log units. So this is 10 to the 8 going from 4 to 12. This is also in logs. So every time we go one of these units, the density is dropped by a factor of 10. Now it's gone to 100, now it's gone to 1,000. The blue and red points are the spirals where we use rotation. The green symbols are the dwarf galaxies where we use other techniques. And here's what you see, that there really is quite a big change in the central density as we go from very small galaxies, very faint ones, to quite large ones. So the faint galaxies have much denser halos. They formed early in the life of the universe, when the universe was much denser. That's why the halos are so dense. And for little galaxies like this, the halo density is about a solar mass per cubic parsec. Now that may not mean much, but here's a picture of our galaxy. Our sun is sort of somewhere around here. This density of the dark matter is 10 times greater than the density of the disk at this place. So this stuff is really, really dense. Okay, this one gets a tiny bit technical, but it's not too bad. As I said to you, the halo density depends on the stage of the universe when the little galaxy collapsed. It actually fell out of the universe. We parameterize that in terms of redshift, which is just how much the spectrums move, but I'll translate that into ages in just a second. The density goes like 1 plus the redshift cubed, so it goes very fast. The faint galaxies have densities about 500 times higher than the larger spirals, so the redshifts of when they actually formed are then in the ratio of the ratio of density is the ratio of the cubes. Take the cube root of 500, it's about 7. So the redshift that the dwarfs fell out compared with the redshifts of when the spirals fell out, the ratio is about 7. So we believe that these big galaxies, for all sorts of other reasons, fell out of the redshift about 2 or 3. Now 2 or 3 means something between 2 and 3 gigayears, billion years after the Big Bang. Life of the universe, 13.6 to 13.7 billion years. So this is quite early. The redshift of the little galaxies forming is around 20. It's consistent with the simulations that we have at the moment, and it means those little guys formed only 0.2 of a gigayear, about 200 million years after the Big Bang. So very shortly after the Big Bang, these guys fell out, and they were pretty much the first galaxies to form. Okay, so now I'll just talk a little bit more about elliptical galaxies and a few other things in the last minutes of the talk. So not all the galaxies are spirals. Some of them are elliptical systems, and they're not really rotating very much. How do we measure gravity in systems like that? This is the biggest galaxy in the Virgo cluster. It's a nearby cluster. You can see all these little dots here. Those little dots are star clusters that are about as bright as our dwarf galaxies. And there's like 10,000 of those, and then you can see some big galaxies here. Okay. One way we can measure the dark material in these is using what's called gravitational lensing. So here's a cluster of galaxies. It's called Abel 2218. And you can see all these arcs. Those arcs are not processing faults or any technical faults. They are the lensed images of galaxies that lie far behind this cluster. And as the light from this little galaxy passes from the galaxy to us, it goes through the gravitational field of this cluster, and the gravitational field of the cluster acts like a lens. It bends the light, and it gives you these sort of arc-like shapes. You can see they're sort of, to some extent, centered on the field of the galaxy. This has become a very big field of study, and people have worked out how to calculate where these galaxies are and how much mass is in the cluster. And it's a very strong and completely independent technique. We use a distortion to calculate the total gravitational field of the nearby galaxies, and the result is similar to the spirals. Elliptical galaxies are about 95% dark and 5% stars. Now, there's another sort of lensing that people use, which is not quite so dramatic. You just get very small elongations of the images, but if you have a few 100,000 galaxies in the background, you can actually work out what the gravitational field is in some region of space. And this is a very dramatic discovery a few years ago. You can see the galaxies, the optical galaxies are these bright things. The blue stuff is dark matter as inferred from this sort of gravitational lensing. And what you see is that there's some dark matter in the middle, and then there's a great ring of dark matter in this cluster. And people figured out that what's probably happened here is that there's been a collision of two big clusters of galaxies. And the collision would have been along the line of sight, along your line of sight. So these two galaxies are sort of moving like that, these two clusters. As they go through each other, there's a sort of gravitational impulse that one exerts on the other, and the effect is to transfer material out into this ring. It's an outward moving ring, and what's going to happen is that this stuff's all going to fall back, and it will just make a mush, and these two clusters are going to merge. But this one has just been caught in this time. This is going to take a long time, take billions of years to settle down, so it's not too unlikely. So it probably comes from a collision of two small galaxies, two small clusters about 2 billion years ago. And the interesting thing here is you can see more or less that the dark matter is actually together with the galaxies. So that was quite a nice one. That prompted a lot of interest. But there's an even more interesting one, which is called the bullet cluster that you may have seen if you read this sort of stuff. This is a more complicated situation. Clusters of galaxies include three kinds of matter. It includes the galaxies themselves, these yellow things. It includes the dark matter, which here is seen in blue. And there's one thing we haven't talked about. In clusters of galaxies, there's a lot of ordinary matter in the form of hot gas. In fact, there's more hot gas in these galaxies, in these clusters, than there is mass in the stars. So most of the ordinary matter in clusters of galaxies is actually in this pink stuff, which is hot X-ray gas. So how was this done? Well, the galaxies you can see, the dark matter distribution came from lensing. The hot gas is so hot that it actually emits X-rays, and it's seen with X-ray telescopes like the Chandra Space Telescope. And this one is very interesting indeed, because what you see is that the dark matter and the galaxies are together, but the gas has been kind of stripped out of the two clusters just because gas interacts. And so we've got the gas detached here, but most of the ordinary matter is in the gas, but the dark matter is actually with the galaxies. And that's not great for MOND, because MOND would like to have the dark matter, or what looks like dark matter, would like to have the dark matter with where most of the ordinary matter is. So this does not look so good for MOND. Most of the baryonic mass is in the pink gas, but most of the gravity is coming from the regions which are blue, where the galaxies lie. Now, MOND works very well for individual galaxies, but it doesn't work so well on the large scales of clusters of galaxies. The only way you can make MOND work is that you actually have to kind of break the whole MOND rule, and you have to invoke some kind of extra dark matter in the clusters compared with what's in the galaxies. Now that's not quite as bad as it might look, because when you get to, remember I said, to form a galaxy, dark matter can't be moving very fast, because otherwise it's got too much energy and it won't condense. When you get to a big thing like a cluster of galaxies, that's no longer true, and you can afford to have what's called hot dark matter or warm dark matter, because it can condense into these huge structures like the clusters of galaxies, even though it doesn't condense so well into structures like the individual galaxies. So hot dark matter is okay for clusters which are much larger than the galaxies. And so people have been saying, all right, well, people who like MOND say, well, one way we could save MOND is we need some kind of extra dark matter in the clusters, not just what's in the galaxies, but something extra. It could be hot dark matter. Neutrinos are a favourite candidate because you can have those because they're hot because the clusters are so large. Neutrinos are very common in the universe, but nobody at this point really knows if they've got enough mass. So this whole subject is in a bit of limbo at the moment. So summing up, where are all the baryons, the ordinary matter and the dark matter? Well, just to give you some idea, okay, baryons are ordinary matter made of protons and neutrons like you and me and all the stuff in this room. The cosmic ratio of baryons, ordinary matter to dark matter is 0.16. So about 16% of the matter in the universe is ordinary matter. The rest of it, 84%, is dark matter. Now, I'm not talking here at all about dark energy. That's a whole extra thing. I'm just talking about stuff we call matter. About half of this dark matter lies in galactic dark halos. The other half is just in space, not condensed in the halos. In the big clusters of galaxies, like the one we saw, the ratio of ordinary to dark matter is about 0.16, just what we should get in the whole universe. So these big clusters are a pretty fair sample of the universe, about the right fraction of baryons and dark matter. But in individual galaxies, the baryon to total ratio, instead of being 16%, it's only about 0.002 to 0.005. So galaxies have lost a lot of their baryons in the process of formation. That's our current understanding. Stars form inside a galaxy, blows out a lot of the gas, and so the galaxies are left only with a few percent of baryons instead of the 16% that they might have started with. Okay, just a couple more slides and we're done. So what is dark matter? Well, we don't really know. We know a little bit about what it's not. We did an experiment at Mount Stromlo in conjunction with people at Livermore here called the Macho experiment. And we were looking at stars in the Large Magellanic Cloud, that's the nearest galaxy to us, and we're trying to detect the gravitational effect of lumps of dark matter passing between us and stars. And we found a few of those, but not nearly enough. And we were able to show that dark matter in our galaxy is not made of compact objects, stars or planets, nothing with masses between about 10 to the minus 7 of the mass of the Sun, that's smaller than the Earth, and about 30 times the mass of the Sun. And that's quite an important range because it excludes almost all of the ordinary matter candidates for dark matter. Failed stars like brown dwarfs, dead stars like black holes, neutron stars, and white dwarfs. So that was quite a dramatic discovery, although it was a bit disappointing. We didn't find what we were looking for, but we were able to say, well, whatever dark matter is, it's not in the form of ordinary matter. And so the most likely candidates, once that was done, that happened around 1998 or so, that the cold dark matter is some kind of weakly interacting massive particles, most of which haven't been seen yet in the laboratory. They go by names like axions, neutralinos, things that are left over from the Big Bang. There's been a bit of a flurry just the last couple of days if you follow the astronomical literature about axions coming from the Sun. We don't know if that's right or not. Probably the most promising candidates are that if dark matter are things called neutralinos, which have quite big masses, around 100 gigaelectron volts, then it may be possible to detect those, even though it's dark matter. They may occasionally give off flashes of gamma rays, very hard radiation, that occur when two of these dark matter particles meet and annihilate. The mass disappears and you just get a flash of gamma rays. The best place to look for these sort of things is in the place where dark matter is densest. And as I was telling you, dark matter is densest in the smallest galaxies, these dwarf galaxies. So people at gamma ray telescopes like this one in Namibia are working hard on this and have been for some years, trying to find flashes of gamma rays given off by these sort of objects, but so far no success. So we're in an interesting situation now. There's a whole bunch of physics experiments going on trying to find axions, neutralinos in the laboratory. There's a lot of work going on at gamma ray telescopes like this trying to find these things, but nobody's found anything yet. The instrumentation is getting better and better all the time. There's a thing called the nightmare scenario, which I will leave you with. The nightmare scenario is that in a few years' time, these instruments are all going to get good enough to detect these kind of objects if they're there, and they won't detect them. And what that's the so-called nightmare scenario. Just what we're going to do if that happens, I really don't know. But if they're not in the form of particles, and dark matter is not in the form of particles, not in the form of baryonic things, it really it's going to push us back to alternative theories of gravity, and it's going to be a very interesting time. Now, maybe next year somebody will find the dark matter particles, but we're in a kind of an uncomfortable period now where something should happen very soon. If it doesn't, we're in big trouble. Okay, thank you.
Dr. Freeman ended with plenty of time for questions. So are there questions? Yes.
How does MOND, the modified gravity, account for the gravitational lensing?
It does okay. It's not quite perfect, but it acts like a long-range force. So the photon is seeing a long-range force which will bend it. Now the details of it I haven't got in my head. People have done MOND lensing models, but I can't tell you just how well they work. But certainly in principle, it should give you more or less the same thing as dark matter does, just because it gives you a certain force law, effective force law.
I'd like to follow up on MOND, this modified Newtonian dynamics, or these two ideas, these particles and the modified Newtonian. Most of this isn't specifically my field in astrophysics, but when I read this, it's usually turf wars over this. Yeah. And the simplest thing to me is that with primordial nucleosynthesis, or there are other arguments for other particles. I mean, and things that the audience may be more familiar with. I mean, this is wasn't a proposed one, but going and finding the Higgs boson and saying our standard model of particles are this. To me, that's always kind of the slam dunk answer as to why, as neat an idea of maybe the math of gravity changes at different scales, it doesn't seem as a robust a framework. So to someone who works in the field, I mean, that's just my attitude towards it, and I would obviously need to have a more open mind or rigorous mind if that's the field that I worked in. I mean, how would you reconcile those comments?
I'd absolutely agree with them. The particle side of it depends very much on particles that have not been seen. The neutralino is in the domain of supersymmetry theory. Don't ask me any questions about that. I'm not a particle physicist, but if it turns out that supersymmetry is incorrect, and that's the way that things seem to be going from the Large Hadron Collider, then the whole idea of neutralinos may well collapse. And these are theoretical concepts. Neutralinos, they're in that supersymmetric domain. So axions nobody's seen yet. Maybe somebody's just seen them just the last few days. So all of this stuff is off in the realm of theory. And if the theory turns out to be incorrect, then we're in big trouble. There's an enormous number of alternative gravity theories. I mean, MOND is it was the sort of first one, and it's a very easy one to talk about. But there's a lot of people working out there on alternative gravity theories. It's not the literature I know about. So there may well be more complicated things than MOND that happen to be better. But it's just, I've just got this bad feeling, and I'm not the only one, that this whole subject's going to go sour in a few years, and we're really going to be in trouble.
Yes. You mentioned the neutral hydrogen surveys to survey for basically like frozen disks and hydrogen gas in the air. What did it show about the H1 presence or H2 presence in dwarf galaxies nearby?
Okay. In the dwarf spheroidal galaxies, the ones that are just old stars, effectively there isn't any. In the dwarf irregulars, they're quite rich in hydrogen because they're still forming stars. So they're the ones we can study, those rather messy, like that green galaxy I showed you. They've got quite a lot of hydrogen in them. Not a huge amount of star formation, but they're too small to have nice spiral arms. But they're still forming stars. So those objects you can detect very easily in hydrogen. But the other sort you basically can't.
So they can hold on to enough gas that you'd expect there to be lots of these hydrogen wells, even if they didn't form these stars.
Yeah, that's
around
right.
these dark matter.
Yeah, but for some reason, every galaxy where we found hydrogen, we also found stars. I don't quite understand why that is.
In your history of the acceptance of dark matter in galaxies, I'm not surprised that you emphasize the radio observations that go a lot farther out. But in this country, at least, the optical observations were very influential. You didn't even mention them. Rubin and Ford,
Yeah.
and then we found out that Harold Babcock had anticipated that in 1939.
Yeah. Okay, this opens a bit of a can of worms, and I hope I don't tread on any toes in my answer. M31 was important in that context. Babcock did this work actually before the war, where he was measuring ionized gas regions, and he showed the rotation curve was extended. And Rubin and Ford around 1970 plus did the same stuff. And that was certainly very influential. There was hydrogen data that Mort Roberts did, also very influential, not talked about as much. The bulk of the work that was done optically in this country and everywhere else is irrelevant to dark matter. M31 is the exception. And the reason it's irrelevant, I could bring up the slide, but you can probably remember how, from your perspective, the rotation curves rose and then they went flat. The optical data typically, here it rises and goes flat. The optical data typically gets to here. And it just doesn't get out far enough to give you any leverage about whether there is a lot of missing stuff or not. M31 is the exception because it was very close. But most of the optical work doesn't tell you anything about dark matter. And that really only came to light in about 1982. But it's again one of those strange things. The work that Rubin and all the other people who are doing optical rotation curves what that achieved. It kept the whole subject rolling. It was greatly misunderstood what they were achieving, and still is in this country for some reason. People just cannot get into their heads. The optical data doesn't tell you much about dark matter. This was pointed out very clearly at a conference in Europe in 1982 where Vera was present. She was actually chairing the session which came up. And I think the people who work in the subject understand that, but for some reason in the US it hasn't really got through, and it may be because there wasn't quite so much hydrogen work done here as perhaps there was in Europe, or it came a bit later with the VLA. But her work on M31 was really important. I'm not belittling that at all. That was very influential for dark matter. Yeah. That's a sound note to end on.
Back to modified
Okay,
gravity.
thanks.
How does it explain the apparent density of dark matter in dwarf galaxies? In other words, apparently it's different in dwarf galaxies than it is in big spirals.
Yeah, that wouldn't come out quite so easily, I don't think. Particularly with when you get to dwarfs and the baryon fractions become really low, then I don't think MOD works quite so well. There are ways you can keep it alive, and this guy Milgrom has been successful at that, but it doesn't work as naturally as it does in bigger spirals.
Well, let's thank our speaker again.